So welcome everyone to another OCP Tap call. This call number 106, and today we have Paul Erker. Paul originally is from Carinthia, Austria. He studied at the University of Vienna as well as ETH Zurich. Particularly, Paul is fascinated by explaining the role of time in physics and the institute that measures. So, with no further ado, Paul, the floor is yours.
And thank you for the invitation to talk here. Yes, this is you saw it because I changed it. Also, it's kind of like an extended version of a talk I already gave at the Mulligan Stew organized by Paul Borrell. And yes, basically I don't have to say a lot more because it was already everything said. Yeah. So what is this talk about, or what I want to talk about is about the question, what is a clock? Or one can also ask the reverse question, whether a single qubit is actually a clock. So for those who might not be familiar with this notation, a qubit is just a quantum bit, so a two-dimensional quantum system. Yes, there's also different representations of these two-dimensional quantum systems in nature. One of them, for example, would be an atom. So the two states would, in this case, be, for example, is the atom in the ground state or is it excited? And this also relates to, for example, atomic clocks that we use as timing references. And the same question one could also ask about an ion. And so luckily I got permission. This is the answer we'll give for this. My answer to all of these three questions is actually no. And so in the following, I think I want to elucidate on why the answer to this question no. Luckily, I got this the permission to actually show this very nice picture by David Nadlinger from Oxford, where you can actually see in the middle between these like two tinsel-like metal bolts that go in this. You can see one small point, which is actually an ion, a single ion that is trapped. And so one of the answers to why such a single ion cannot be a clock is if we think from kind of like the information theoretic sense, the quantum information theoretic sense, is like what information can such an ion provide us in the sense of timing information. So some of you might know one can represent the state space of qubits, quantum bits, or two-dimensional quantum systems by here. Smaller than one is a valid state. So let's assume we start out in a state that I just by this red arrow. And what does happen after basically I let the system evolve for some time? I think this, yes, the system just changes to a different state, which is ideally perfectly distinguishable from the initial state. And what I get out after I can, because maybe I know the Hamiltonian of the system, and what I can get out from this is from a timing information, but it's a very specific timing information in the sense that it gives me information about a duration, and it's just a certain duration. So that's why we actually tried to kind of like distinguish two notions, namely the notion of a clock and the notion of a stopwatch. So what a single ion or a single qubit or a single system definitely is a stopwatch. So it can give me, I want to time a certain duration. A single system will allow me to do so. So from this, obviously the question follows, what is a clock. And the first thing I kind of like came up with during my master's was this the model that I dubbed the quantum hourglass. And the takeaway, or like the only thing I really would say back in these days, was that a clock at least needs to be a Piper-type system, a system that consists out of two parts, namely a cursor or a clockwork system and a register system or clock hand system. Because only in this way one actually has one system that one references the time to, or the passage of time, and the other one which basically keeps track of this in the sense of timekeeping, and also allows us to fulfill the basic properties of a clock, which is to continually provide a time reference to an agent, rather than just providing the information about the length or magnitude of a certain just part of this time or duration. I would have saved a lot of time if I would have known that actually David Allen, who lends his name to the Allen variance that most of you probably will be very familiar with, had already written very similar things in a manual that was given out with the HP atomic clocks. Probably also familiar with the fact that that HP used to produce the standard frequency references for a long time until they sold the business. And in one of these Hewlett-Packard application notes, they basically already stated the same thing, in the sense that what one needs to keep time is a reference and a counter. So basically keeping time is a counting operation, but one wants to reference this to physical processes. Although this already captures kind of like something that I think also the quantum hourglass in essence does, that this kind of a clock is essentially Piper type, I do not agree with the fundamental, like the depiction of elements that are necessary here in the sense of an oscillator or an atom. And so if we don't do, or like this also poses the questions, what are the essential elements or constituent properties or constituents that one needs in order to construct a clock? And here I put already autonomous in this title, because this will already hint at actually how we want to construct our clock models from first principle. And autonomous in this sense, like loosely defined, means without external control. So something that we want to do in these models is constructed from first principle, but also make sure that we can actually fairly bookkeep all our resources, and don't smuggle in timing resources kind of through the back door, which actually a lot of times happens, especially in these microscopic models. Okay, so what are these constituents? So as I said, we don't want any external control. We don't want to time our timekeeping device. We don't want to time, or we don't want to exert, start basically from a principle where we take something time invariant, and then use various of these in order to construct or like be able to reference to a physical process where time passes, and we can actually extract the information about this passage. And one of these, some of you might also be familiar with thermodynamics. One state that fulfills this property is the thermal state. It's time invariant. It's given by the Boltzmann distribution over the energies in the energy eigenbasis, and one does not. It's basically omnipresent, and one does not need any timing information in order to prepare such a state, because through the natural tendencies of all systems to accumulate, one just needs to wait long enough in order to thermalize the system and therefore have the system being given in a keep state or like in a thermal state at temperature. Theta here stands for the inverse temperatures. So it's like 1 over T. There's like I set all constants to 1, just if you wonder, like KB, H bar, and also C will be 1 in the following. Okay. But just having something that a system that just sits there in this invariant under time does not allow us to build a clock yet. So what the first kind of key ingredient that we need is actually out of equilibrium resource. And we will see later how we can construct this from these thermal states. Just to give a hint already, this is like if one has thermal barbs or states at different temperatures, one will already induce a heat flow if they're in contact. And this is, for example, an example of an out of equilibrium resource. Or more classical, one could imagine the spring that one winds up in order to have an analog clock run, or the battery of a digital watch. And then, so now to kind of like with this out of equilibrium, we actually have something that evolves in time, something we can reference the passage of time to. And so the second necessary ingredient in order to build a clock is actually to also be able to retrieve this information. And therefore we need an irreversible process that makes us able to actually measure and store the information about this passage of time. Yes. So I think if you have any questions, if I go too quick or too slow, please let me know. I'm also I have time to stay afterwards for some questions. Okay. So given these two fundamental ingredients, out of equilibrium resource and an irreversible process to actually mitigate the tick production, and the ticking or the ticks of a clock will be basically the fundamental unit in which we will measure time. So this is kind of like a visualization on like a basic model on how to envision such a kind of like autonomous clock that one can construct. And you will see the notation or the kind of how we denote these systems also changes. And yeah, it's sub-ideal, but this is still a very young field. So forgive us for this, please. Okay, but you see, like what we had first as basically the cursor system, or let's say clockwork system, which is the system that we want to reference the passage of time, or where we take our reference about the passage of time from, basically needs to have some out of equilibrium and therefore also produce some waste due to the loss of quantum thermodynamics. And then how do we communicate this to a register where we store this time information is basically through this irreversible process that allows us to kind of extract this and gives us the necessary asymmetry, analogously to, for example, like an hourglass, where it's very unlikely that the grains of sand jump backwards. Okay, and so what we did in one of the first works in this direction is we tried to analyze the limits of timekeeping given such a model. And for to this end, we basically used previous results by Paul Skripczyk, Nicolas Brunner, and Popescu, like now they're in other place, but back in the days, where they basically constructed a minimal autonomous refrigerator or thermal engine. This is, I don't think I have a pointer, but you see the above, like the kind of like little squares, they denote qubits. the egg-shaped red and blue boxes denote heat baths, and so one has like two qubits. One is coupled to the hot heat bath. One is coupled to the cold heat bath. And if they're in contact, one can take a third system, which is an equally spaced energy ladder with a metastable top level. So this top level actually has a decay probability. And this decay into the vacuum field is the irreversible process that we used in order to produce the ticks of the clock. And so kind of like running the fridge in the reverse mode. So it's a heat engine through this heat current between the hot and the cold qubit. One can actually drive energy back and up this ladder. And then when it arrives at the top level, it basically decays into the vacuum, and therefore and timing information is carried away by the photon that represents the tick. And this is what one can probably call like a minimal autonomous clock model. Here again, that's just kind of like the energy structures, and also shows the resonance condition. So this can only happen if the difference between basically the excitation from the hot qubit that is dumped into, let's say, the cold qubit, or actually together with the ladder, such that we have energy conservation, or actually energetically enable such a transition. So before we discuss further what we actually can extract from such a model, or what does this model tell us about kind of like fundamental limitations of timekeeping, I think an important thing is to actually also introduce figures of merit, and also so that we're able to kind of like compare different clocks to each other. And so we defined these two figures of merit that we think are important. Especially the resolution is very dear to me, because this is a lot of times forgotten in, let's say, more information theoretic approaches to timekeeping, that things actually happen at a physical scale. And so in this case, R, the resolution, is just 1 over the expectation value of the waiting time. And the second measure, without accuracy, which also leads to a lot of confusion sometimes, is basically something like a signal to noise ratio. So that's just the mean or the average over its standard deviation, or the variance squared. And in the limit of infinite, like of going to infinity, this actually turns out can be interpreted as the amount of ticks this clock can tick on average until 2 of these ticks are, or the uncertainty between 2 ticks gets as large as the distance between, the average distance between 2 ticks. There has also been work before which also tries to do this even more operational or more abstract way, because here to some extent we still kind of like these 2 figures still depend on the existence of a background time or a perfect clock with respect to which one actually evaluates these measures. Yeah, still I think like something that a lot of interesting things came out of this initial model. Namely, what we saw is here new tick is actually kind of like the rate. So it's 1 over the tick time. And QC is basically a proxy for the energy or like the entropy dissipation or the energy cost of this clock, because it's all the energy that one dumps into the cold bath and is not able to retrieve anymore. We just assume for simplicity that we can actually perfectly recycle the energy that is carried away in the tick by means of the energy of the photon. But what we even ignoring this, like one wants to bound the most ideal case, and even here we see that in this model, one can actually let's say has a trade-off that if one wants higher tick rates, a greater resolution, one actually needs to dissipate more energy. And this also depends, as we will see, on the given accuracy of this clock. And so here we see that the accuracy also scales with, like, until the curve saturate, but scales with the dissipation of this clockwork. Namely, that if one wants to build a more accurate clock, one needs to more entropy into the environment. And here we also see that this all depends on the resolution of the given clock. And so lastly, we can also like plot the resolution against the accuracy. And we see that there is a trade-off relation that for a given, so each of these curves to the right represent a given energy or entropy dissipation per tick. And one basically has a trade-off where either one can invest kind of like this cost into having a more accurate clock or a better resolving clock. And I think this is already quite interesting. And this, like at least for the holds for this model, for one of the first models that we came up with. Exactly. And then in the special case that we let the dimension of this energy ladder that is shown here with the spacing let this go to infinity, and also let the temperature difference go to infinity. So like the cold bath is at 0 temperature, the hot bath is at infinite temperature. One can actually derive this very nice result that there's an upper bound to the accuracy in this idealization, and it is given by half of the entropy production per tick. Back in the days, we thought that this actually hints at a more universal behavior, but as we will see in the end, this is actually not the case. And it turned out that although we fully, genuinely, like we describe this minimal autonomous quantum clock in terms of quantum mechanics, it actually acts as somehow like a classical clock, although it's a little bit ambiguous what classical means. But it seems that this is actually a bound that holds for yes. So then we try to make these clocks better. And one thing one can do in actually to be able to build better clocks and also reduce the entropy production per tick. So like the efficiency of producing ticks at a certain accuracy and resolution, is to do something we call as temporal probability concentration. Because, for example, like one of the simplest examples of like something one can reference time to is just a thermal process or a decay process. In this case, it's like I can put an ice cube on the table and then have a very coarse understanding of the passage of time by letting it melt. So this is a very simple, but it's also a very bad clock. So basically, like the resolution is kind of like how finely can I distinguish the different sizes of the cube, or I just get kind of like let's say a coarseness of hours. It's like if I would just want to distinguish, it's like half melted and so on and so forth. But what one can do, and in this can we basically kind of like make this ice cube, and here we put like the Swiss train clocks. Maybe it should be the Japanese train company clocks if they have equally, because they're actually even more on time. But can we turn this ice cube into a very good time reference? And this is actually what we want to do with this temporal probability concentration. And so one way, this is from the PhD defense of Emanuel Schwarzan, which is one of the is one way. So one can imagine an hourglass again. And so then I basically have to pay for each grain of sand, 1 grain of sand. But if I have some other process, for example, here a flywheel with a little hole, I can actually restrict the ability of the sand grains to go through by kind of like the time it takes for this hole to pass, and therefore concentrate the tick probability to a certain temporal region. And I will get away, like if I just sit at the lower end and I count these grains, they might not come as often, like depending on how fast it spins, but they will definitely come more accurate. And so then this leads to basically another question. So we show you then also how we implement this the autonomous the temporal probability concentration. And what we see is that there is actually a connection to the complexity. So this is kind of like an overview slide. Again, we have like we start out with our time invariant resources in terms of thermal baths and states coupled to it. And then we see that will, depending on the complexity of the clockwork, we will get different waiting time distributions for these ticks. In the sense, the more complex our clockwork is, and we see this already on the left-hand side. So here, for example, this P top would be kind of like the occupation or the occupation probability of the top level, the population that is present. And in terms of an ice cube, this would be just constant. While the middle section is actually kind of like corresponds more or less to like the first model I showed, where we just have like this simple 2 qubits or 3 qubit system, or 2 qubits in the energy ladder. And we're able to kind of like periodically drive this up. And now we'll see that we can construct complex clockworks that actually allow us to shape this probability distribution, or this probability density function in time very neatly. And as we kind of in our models, only the top level decays, we can actually restrict the ability of the system to produce a tick to certain very, very narrow regions in time. And this is the model we used. So each of these machines with the sub super index represent one of the machines that we used in the first model. So we have they're coupled to a hot and a cold bath, bringing them in contact in resonance with the transition of the ladder, makes them able to cause an excitation of this ladder. But now the difference is that before, basically one machine was driving all the transitions of the ladder. Now we actually have not only one machine for each transition, but we can actually use like a rectangular extension where we use M machines that are coupled to one of the transitions of this energy ladder. And they're coupled in such a way that they conditionally excite this transition in the ladder. Namely, if machine 1 did not give off the excitation to the transition, then machine 2 can do it. If 1 and 2 didn't do it, then machine 3 can do it, such that we can actually like control very neatly for how this energy packet actually travels up the energy ladder. And this is what we see. So in this case, of course, because complexity is a very widely used term, and it's also not clear in most contexts as how to actually calculate this. Here, as a proxy of complexity, we take the number of machines M that couple to one transition, and this times I mentioned already kind of like gives us a number of the total number of machines that we use to implement this clockwork. So taking the number M as a proxy for the complexity of the clockwork, we see that we actually can like only give like there's for certain values of m, we can only reach certain accuracies, and the higher the complexity, the also higher we can actually drive the more accurate the ticks are that we can produce. Yes, and so this, to say to this, maybe I just want to say that there's unfortunately kind of like a little kind of like a mistake that we did while doing this analysis, which was to forget about the back action that actually kind of like the measurement of the photon or the emission of this photon has. Is something we work on, but as far as we can see, it does not qualitatively change our results. But the numbers might be off a little bit. Yes, but it's something we work on. Then we had a master student that joined us, and one of the tasks we gave him, or the idea we had to solve, and he did so brilliantly, was to actually like look at the signal, or let's say the best possible clock, given these two ingredients. And what he came up with is this beautiful equation, where he basically derived a fundamental bound on all timekeeping devices where the tick production is mitigated by an irreversible process, in this case, decay process. And we took an exponential decay as this process because, we don't know, as far as I know, there are no fast decay processes. So basically, this capital gamma is the rate of this process, m still is the accuracy, r is still the resolution, and what we get is that basically the accuracy of any timekeeping device is bounded by the speed of the tick mitigating irreversible process, and also like limited by the resolution. Yes, and this is like not super recent, a year and a half ago, but this is like really general. And then already hinted it at before, we see that there's actually two regions that we can define, because something one can always do, and somehow it's kind of like intuitively done, and also kind of like very well researched in terms of atomic clocks, is that one can average over certain amounts of ticks. And that's also to some extent how atomic or optical clocks, or in the future probably also nuclear clocks that are being developed, measure actually time averages. In this context, it's mostly called the integration time. And if one does so, then the blue line holds. So if I start at any kind of like point, I can always like bunch ticks together. So instead of considering each individual tick, I can consider every 10th tick kind of like, let's say, the big tick, and take this distribution, and therefore have more accurate ticks, but at the slower speed, and therefore at the smaller resolution. And this is like, although it's not completely clear, but what I will now do is like basically refer to these clocks as classical clocks. But then we see that there's this other line which is given by the bound that I showed before, and this bound actually is squared, so it scales way better. We also think that we can that are situated at some point of this line. Yes, and this I would call quantum. But yeah, sometimes it's very ambiguous what we actually mean by these terms. And so then we see the outside region is actually forbidden. So we could have colored it. This is a region where no timekeeping devices that function this way actually can exist. And so what we did and what we're still doing is actually look, as physicists, is like look for expressions of like these models that might be nice, that might be of interest to theorists, and also might kind of like lead to deep insights about the nature of time in the future, but for the moment just remain kind of tools for us to realize this, because one has to start from somewhere, but also look at kind of if we can find representation on in nature that kind of allow us to kind of like find evidence that these models are actually useful or describe somehow processes in reality, in nature. And we found this in the group of Natalia Ares, who's a professor in Oxford and runs a experimental group there. And in their experiments, they can basically take a membrane, like a very kind of like a thin sheet that's approximately 10 atoms thick, and extend it over 2 gates. And this membrane kind of like we will kind of like try to identify this with the model that I showed you before, where we have this membrane. And that was kind of like the beginning of the operation, is them giving a talk about an experiment where they can actually feed or like drive this membrane with white noise. And so this would be kind of like our heat bath, the source of energy that allows us to kind of like keep the clockwork running. So then the membrane will start to oscillate, and these oscillations can be read out by this tank circuit, where they show up as oscillations of the voltage, because like depending on the position of this membrane, the capacitance of the system changes. What we saw here is that something in the same direction as we derived in the first model of the minimal autonomous clock, that with higher power we also get higher accuracies. Here the different lines represent different or different power levels of the readout tone. So that was something where, unfortunately, this is more or less a test bed for these kinds of systems, because one still had to kind of like illuminate the cavity, the membrane cavity, with this readout tone, because otherwise there was no way on how to actually read this out in terms of autonomously without having to actually input the frequency. But this is something we're still working on also on different platforms. But so we see that with increasing power, we actually get higher accuracies. And then like if one plots them against, so we derived, because it's actually a mesoscopic system, so it's not quantum, it's like basically classical. So we can derive basically expression for the optimal accuracy one can achieve with such a system. And we see that all of the measurement data basically lies on this line, which is 1/10 of this optimal theoretical bound for these systems. Yes, but this still agrees very nicely with what we see. Yes, and so yes, this is still a story to be continued, and we're still working with several with Natalia Ares group and also several other groups. I come back to a more theoretical topic, namely the relation between timekeeping and computation. And this is probably also not let's say, does not make so much sense from a completely information theoretic perspective, but because there you just have steps, and if one has these steps, maybe one cares about how many steps, but timekeeping would not necessarily play a role. Maybe for you it does, because from seeing it also like in classical computation plays a huge role. But in quantum mechanics, it's actually at the foundations of these computations, namely each of these logical gates that one can apply in a quantum circuit model, represented by these matrices, and which basically form the basis of universal quantum computing, in reality basically amounts to a unitary, which in physically has to be implemented by letting applying a Hamiltonian for a certain amount time. Here I denoted tau, so tau not only stands like is used for the thermal state, but also for a duration. So each of these gates physically actually have to be implemented by turning on an interaction and turning it off again. And then the actual rotation or the actual gate applied depends highly on how long I apply this gate. And so we try to kind of like, let's say, quantify this also. How does this kind of like, if one accepts the fact, which maybe I should have also mentioned before, is that all the previous results basically imply that something like a perfect clock does not exist, because it either never ticks, so it has a resolution of 0, or it would need infinite entropy reproduction in order to have an infinite accuracy. But so to quantify this, the impact of this of the imperfect timekeeping on the computation, we came up with, or like Jake, who spearheaded also this effort, we basically derived this model where we kind of like slice up the whole quantum circuit into slices, and in each of them, and we just did it for C naughts, or like because these are basically kind of like the heavy computation, but one can in each of these slices apply an arbitrary number of other gates, and they're controlled by a clock that has a certain accuracy, and then we see that depending on the accuracy of this of the clock that we use in order to control this interaction, we are limited in that we limit the number of gates we can actually apply, given that we require a certain fidelity. So we see this in this heat plot, where the color denotes the fidelity after the computation. So how near is my final state to the one that I actually wanted to produce? And then on the x-axis we have the number of gates. On the y-axis the accuracy. Yes. So, and here we see, like for example, in the inlet C, that kind of this also quickly saturates, and accuracy of 10 to the 7 is already enough to apply a lot of gates. Or if we go 10 to the 10, we're probably able to apply most of the number of gates that we actually want to apply. And this also like is I think like one of the first, or let's say, important push on the theoretical and foundational level. Practically, normally in experiments, the timekeeping budget or the error budget of timekeeping is normally pretty low. Yes. And so this talk, I think I gave actually like in this form back in June at the Atomic and Molecular and Optical Physics Conference in Rhode Island. So here there's still the archive link. I should have changed this. It has been published in a peer-reviewed journal already. But so then I basically ended this talk. No worries, it will continue a little bit more, because we have a lot more new results in the meantime. But I ended this talk by like basically asking the questions that I'm still very interested in. It's kind of like the first question hints towards the connection of all of these models with modern frequency standards, atomic optical clocks, where basically like most of the engineering over the last decades went into how can we prevent the drift of these devices. And this is something that's inherent to laser. And now all these limitations we actually derived, they were still in an idealized scenario. So because like none of these frequencies, none of the energy levels, like they were all assumed to be perfect. So like even in this idealization, we already see that that there are still limitations that stem from more fundamental facts. Exactly. I showed you the two regimes of the fundamental bound on timekeeping. And the other question is like, can we like on the red line, which is like the optimal scaling, can we actually like find for each of these points of the line like an implementation that actually guarantees this scaling? Because like I would say gamma, this capital gamma, is normally something that we have to take that is fixed, because like decay, there is no way how we can, or at least I don't know of any ways how we can actually shape those. It's something that we kind of like decide, we search for. I take this transition, it has a certain decay rate, but then can I find kind of, can I this optimal scaling? And then something that that these optical like or atomic clocks also rely on is our feedback mechanisms, and this is something we also have not taken into account in an autonomous fashion yet. And then the last question I will actually answer is, can we use these clocks in the sense where we showed that this timekeeping affects the computation? Can we actually find implementation where we control a different system, where we can implement one of these? Sorry, I have the zoom went exactly, where we can find a explicit description where we can use a clock to turn off and turn on and turn off an interaction, or like a Hamiltonian of a system, in order to implement actually a quantum gate in a way that it's not externally controlled. And yes, and then last but not least, like all these models are nice, but I think what's still also missing to some extent is there kind of like a physical limit that is like non-trivial, in the sense of not being like of the order of Planck time, to the stability or the accuracy of clocks that we can build. Because like in theory, as I said, like our models, they don't include any drift. So in theory, we could always like go down the blue line on the left and just average over. But as we see on the right-hand side, is like all of these timekeeping devices in a certain regime, a very kind of like low frequent noise sets in that cannot be corrected for anymore. And this actually kind of then leads to this minima. In here, it's the Allen variance, or Allen deviation is basically the inverse of the accuracy, kind of leads to the fact that the Allen deviation always kind of like bottoms out at some point. And averaging does not help anymore. Yes. Okay. So this was like the advertisement. So actually, I'm in the US right now, in Illinois, at the University of Urbana-Champaign. And next week, we'll go to the Quantum Thermodynamics conference, where some of the work that I will present in the following is also present. And then if anybody is in Europe, would invite you to come to the Time in Quantum Theory conference, which takes place in a castle in Slovakia. And I think they're already open for registration. And I think there's a lot of interesting talks that revolve about this topic. And also, we always try to invite like experimentalists that actually build clocks to kind of like enable a discussion and collaboration between the different communities. These are the references to all the works that are presented, and also to our group homepage. Yes, and then so this would be the end of the first part, which was a year ago, and then this continued. We didn't stop thinking about this, especially the last question, which I said we can affirmatively answer. We did, but again, I would like to kind of like give like a little flavor for what is the regime we're like super interested in, and therefore we kind of like try to conceptualize this. This is Jake's drawing, who was also the first author of the work about the imperfect timekeeping. And so we think of this in two different regimes. So there's the non-autonomous computation, where basically one has external control over, for example, the gates. I can actively flip stuff, while an autonomous computation, and now like in the classical regime, would be, for example, something like the billiard model, where I just place the obstacle
they encode my program. I have all the balls coming in with a fixed momentum. And then depending on where they come out, this gives me basically the result, the output of my computation. And then we have the quantum regime, where if one imagines kind of like very common platforms that are used for implementing quantum computations at the moment, trapped ions or superconducting qubits, and so on and so forth. One has to always kind of like have extremely well-timed control over the systems by applying certain like pulses at a certain frequency to actually implement those. So this would be either like a laser pulse or a F pulse in the like laser for, let's say, trapped ions, or a laser pulse, RF pulse for in the case of superconducting qubits. And this, to some extent, is also, like in the case of superconducting qubits, is one of the limiting factors at the moment, because it inhibits scaling in the sense that for each of these, to be able to kind of like bring these controlled pulses to the place where, like, to the physical implementation of the qubit, one needs to have a cable that runs all the way out of kind of like a room temperature environment into all the stages of the fridge, where normally you have like different stages, kind of additional electronics to actually kind of like manage those. But basically what one does is like this, that in a superconductor qubit, they need a very like well-controlled supercode environment, and one introduces these cables that bring extra noise. And so this is actually detrimental. And also one cannot put thousands of cables into this device, into these fridges, because this would basically then also ruin the fridge, and that's physically not enough space. This is mitigated by multiplexing these channels, but it is something that actually limits the amount of qubits one can put on one of these chips in one of these fridges. And so on this quantum level, the autonomous regime, we imagine, like, for example, like hard-coded interactions with these paths and all of these little machines that drive the clocks that drive the interactions. And so here's another illustration of how we kind of like model this autonomous computer, which we call a QPU. So it's driven by, again, hot and the cold heat bath, which gives us this kind of out of equilibrium resource that allows us to basically run a clock. And then A here basically defines the program or a punch card state that inputs what kind of operations we want to implement on which of the target systems. And so here in purple, that's the target systems. And then there's a conditional Hamiltonian that basically for a given tick implements one punch card step after the other, such that in the end we end up with this UA, which is basically the computation we wanted to perform, and this is basically the output state. So it's really like back to the spirit of a classical input-output model of computation. I did not put a nice illustration because I'll maybe add it afterwards. But something that we see here is that we can derive limits for the speed of a computation in such an autonomous fashion. And FA is here again the fidelity. So like how near is my end state to the desired state? This is bounded by 1. And we see that kind of like the thing that we have to subtract, the big O notation just means of the order of, loosely speaking. M is the number of steps we want to do. Nu is the frequency squared of how fast we want these gates to be applied. Gamma again is basically the rate of the tick mitigating process, and phi max is the maximum angle we actually want to move in this phase space. So like one can imagine this all these logical gates, these quantum gates, being just rotations in the phase space, and this basically spans the maximum angle. So the further we want to go in kind of like in the phase space, and the faster we want to go, the less fidelity we get. And here is kind of like let's say the simplest example that can be thought of, namely like the creation of the Bell state. This is just the application of let's say 3 different steps. And then we see here that basically each time step, when a tick occurs, the autonomous quantum computing unit implements a gate, and then in the end we end up with the Bell state, in this case the psi plus, and then we basically require the punch card to always have enough idle operations in the end, such that one does not need to require an additional clock to kind of then know when the computation is over, but one can wait, let's say, sufficiently long, and then one will find the autonomous quantum computing unit in an idle state with the output state already ready to read out. Yes. And something also that an effort that was spearheaded by Florian Mayer, who already mentioned before, is he came up with like a model that actually goes far beyond the limitations that we have seen before, where for this kind of like, let's say, quote unquote, classical clocks, we're limited, the accuracy of these clocks are limited by half of the entropy production per tick. This is a model where this is not the case. And to the left, we see that basically this clock consists out of a spin chain. So these are all coupled systems, and we introduce 1 excitations that then can coherently travel through this chain, and in the end is emitted, and the whole process starts anew. We require that there's only 1 excitation, so this kind of like latching mechanism is shown in P that should in inlet B that should guarantee that there's only 1 excitation traveling in the ring at all times. And then we also see that we basically like we count the number of photons we get out, and this gives us these are the ticks of the clock. And in inlet D, there's the different coupling constants that actually allow for this behavior to be well, yeah, like one has to actually prepare the excitation and this wave packet traveling through the bulk, because it should be actually spread, so it's like very narrow in the frequency space, and then in the end one has to also prepare it to be able to be absorbed. I think it's called apotization. Yes, but what Florian and Yuri could actually show in this model was that the accuracy in this case, in this model, is actually not linear in the entropy production, but is exponential. So this sigma is like so basically what we get is a accuracy that is not bounded anymore linearly by the entropy production, but only exponentially, which basically means that this scales a lot better. Yes, and so these are the references to what I told you about the autonomous quantum processing unit. And the second one, which is the ring clock, where one can actually derive accuracies that are not limited by the entropy production linearly, but only exponentially. So that basically like the accuracy scales exponentially with the entropy production. And then I also wanted to mention, this is like work that came out also very recently in June, and this super interesting work along the same lines. You will see we're kind of like still a very small community, as most of the names overlap in these references quite often. And one is the optimal time estimation, and where they basically come up, they basically analyze how we optimally can describe, or what are the optimal, let's say, estimators for counting different currents or counting different kind of like stochastic processes that are the origin of these ticks. And the other one is or a work out of Zurich where one can use basically like the worst possible clocks in order to still kind of like compare clocks and other clock signals with it. So it's kind of like going really to doing fundamental analysis on and how we can process these this discrete timing informations. Yes, and with this, I would end my talk and say thank you for your attention.
Thank you very much, Paul. Okay, let's open the floor for questions.
I have a simple question, Ahmed.
Yeah, go ahead, go ahead.
How we can synchronize quantum clocks?
Yeah.
Hello.
Hello. Sorry, I had my. I hope you heard me during my talk. I had this on.
No, we heard you. No, like so basically the question Sham is asking is like, how do you synchronize now, let's say, two entities of this clock?
Yes, that's a very good question. And I don't have a very good answer. So of course, like the more accurate these clocks are, the easier it is synchronized, and that's also basically one operational measure for the quality of a clock is how long. So this is called the alternative tick game. Is like how long, like in a game theoretic sense, you played with two clocks and you want to kind of like tick-tock your signals to a referee, and how many rounds you can actually win this game on average. And to some extent, synchronized can be used as a measure to quantify the quality of clocks. But yes, like how to use these, like any specific protocols, I could not answer now on the spot. I would refer to a lot of literature on, and there's a lot of times there's a jargon problem, and a lot of this literature is sometimes comes under the name quantum reference frames, where one tries to do this. Yes.
But if the two quantum clocks are entangled, maybe they will be synchronized automatically, right?
So one thing we have not managed, I think it's also not, the entanglement normally helps in all communication tasks. It funnily does not really do to help you to construct a better clock as far as we know. But it does help to synchronize, yes. They're not automatically and they're not perfectly synchronized, but there has been a lot of work in the recent, let's say, 15 years, constructing explicit protocols for using entangled and also multiparted entangled states actually to create a high level of synchronization.
Thank you.
Yes, but what I have to say is that something that I, like, as I mentioned in the beginning of the talk, is I distinguish between stopwatches and clocks. And most of these protocols actually don't use clocks in the sense that I use it, but they use kind of like the synchronize actually stopwatches. So basically the rotation of these systems. But of course, if you have many of those, like a collection of stopwatches also gives you a clock. So there might be like it might practically not matter.
So I've got a quick question if you have time.
Yes, sure.
So thank you, Pauli, for an absolutely astonishingly good talk. Thank you. I always learn so much from you. So you said to produce 2 clicks on the clock, you mentioned that you need 2 things, an out of equilibrium resource and an irreversible process to retrieve it. So my question is this: does this notion of out of equilibrium imply that there is a stochasticity in the direction of time?
I would not necessarily say so. I would rather say that the irreversible process normally implies a stochasticity in the production of the ticks. But yes, like, so of course, I would love to be able to say things about the nature of times, but it's a very hard problem, and normally one runs into tautologies very easily and very quickly. And so that's actually why we construct this clock, so we can at least say something about how we measure time and not so much what is the nature of time. But maybe we'll get there one day, hopefully.
Thank you. That's a beautiful answer, and it's really thoughtful and helpful for you to, kind of admit where the community of physicists are in terms of understanding these problems. There is, of course, a great deal of tautologies and philosophy that gets argued about on these. So my next question is, how do you manage cycle slippage, and would you know it even occurred?
The tick slippage.
Yes.
Yes, that's actually one of the worst things that can happen. Is like for one tick to slip. I would certainly kind of like impact the accuracy the most. Like we don't have any, let's say, explicit construction or protocols on how to account for this, except that it, like if there's always a probability that it happens, we account for this probability, it influences the accuracy, but we don't have for an explicit construction of a clock, like something that takes care of this. Like maybe I go to one of the last slides where we have this kind of on the top right, we see that actually like also we changed a little bit our approach to how we count this, because like in quantum mechanics, everything kind of like also has the reverse process, also has a probability of happening. So one cannot construct perfectly unidirectional, like in the temporal sense, processes. And so here actually it can happen that kind of like excitation kind of like goes in the reverse direction, and we actually have to count this as -1 tick, or like kind of like the register kind of like unwinds, or that would be kind of like in a classical sense, if you have the regit and then basically kind of like it jumps out and goes back to 2 seconds, for example. And of course you want to basically construct your system such, and that also gives you the highest accuracy, that there is no slippage in ticks, and also kind of like no unwinding of the regit. But I would say, yeah, I cannot give you a protocol on how to solve like handling these, but yeah, I would say that we try to just construct our clause such that they don't happen.
So if I may, I have one last question. I know that we're slightly over time, but this is particularly interesting to this audience. Do you have any thoughts on indefinite causal order and how that might manifest in the behavior of clocks, say in a data center that has IEEE 1588 precision time protocol or better?
I don't have an answer. I can just basically like comment on what I think is still an open question, because of course, like there's a lot of like, this is one of the open questions that kind of like, I would say, come out of quantum mechanics. You have to give me, I think, or you're basically, I think, very active in researching the connection to also kind of like the effects, or like how this relates to the timing data centers. But so like we know that if we kind of like loosen, for example, the only thing we require is that locally quantum mechanics holds, and we kind of like don't assume anything about kind of the space-time structure or kind of like the ordering of events outside of our kind of like local lab or the room that I'm in now. Then we get these very general processes that are kind of like still respect this condition when we have like 2 of those, your room, my room, that go far beyond what we see that is expressed in nature. Or let's say, at least we cannot observe processes that are so general. But this is also still a area of active research, and it's like so far I don't think there's any experimental evidence that these more general structures actually manifest in nature. But it's a very interesting direction of research because it might give us answers about kind of one of the big kind of like let's say missing connections, which is kind of like to bring together relativity and quantum mechanics. And this is one of the approaches that might be fruitful.
Thank you.
A quick question.
Yes, please.
Paul, thank you very much for your fantastic presentation. Do you think that you will benefit from the topological materials that were announced at the beginning of this month, and specifically those that exhibit a complexity of 1.58?
Oh, not. I was traveling the last 3 weeks, so I'm not familiar with.
I'll send you the source. It was in Nature Physics.
Okay.
Unbelievable stuff.
Okay.
And specifically your sensitivities to temperatures, sensitivity to noise. I think that I see tremendous benefits along the lines of your interest. Thank you.
Yes, I like please send me this reference. I would be very happy to have a look. And yes, like for the moment, we're like when it comes to kind of like finding systems where we can actually see this behavior or engineering really autonomous quantum clocks or such really ring clocks. Yeah, we're trying to do it in superconducting qubits at the moment.
Yes,
yeah.
I feel that specifically the autonomous approaches would benefit tremendously.
100%. And like to some extent, that's kind of like the dream to in the end kind of like really be able to build this stuff and have it modularized in the same kind of like or in a similar fashion that now classical computing infrastructure does not require to design every part anew once you have it, but you basically have all this module you can collect together, and collectively they give you a very potent system. And I think that clocks are one of the, let's say, fundamental, like the backbones of these structures, classically and quantum.
Yes, that specific reference has appeared now already in your chat, so I won't have to send it to you. Thank you.
Okay, thank you.
It's one of the new developments. Yes, thank you.
Mm-hmm.
All right. Any more questions?
I just have a thought. When you're referring to the 1.58, I'm familiar with the work that's been done on machine learning in particular. And the basic idea is that instead of just looking at plus and minus 1, you have to introduce 0. And then, there's all sorts of interpretations of that. But for the audience's benefit, this it turns out that 1.58 is nothing more than, the logarithm base 2 of 3, which is ternary logic. I don't know if
no, it is the complexity of the structures themselves. Okay. It is from the space filling components, not an algorithm of 3, and it is not limited to base 3.
Fantastic. Well, I'd love to talk about that in Mulligan Stew in 2 days from now. If you're around, Wiltold, that would be a great conversation.
All right. So any more questions? If none, just want to let you know that there will be another OCP Tap call on coming Monday on 9 a.m. And then like the usual time also is like the one in 2 weeks. So the one in Monday, I won't be available. Hasham will run it. And I'll be back with you guys on the subsequent one, which will be call number 108. So as usual, the calls will be like the recording will be available on the wiki alongside with the slides. And thank you everyone for attending, and thank you, Paul, again for the great presentation. And see you everyone on Monday and in 2 weeks.
And
All right.
in the Monday meeting is also about quantum communications. So it will be
Yes.
related to what Paul is talking about. So good coincidence, Ahmed. Thank you.
You're welcome.
And I'm planning to be there too.
Yeah,
Wonderful.
Thank you, Hashim, for organizing that.
Yes, thank you for the invitation.